So in this video, we're going to do an application example utilizing sum to product or product to sum formulas. So I want to preface by saying I am not an electrical engineer. I have never taken a course in electrical engineering, so I have a very basic understanding of some of these concepts. But I talked to some electrical engineers when I was coming up with this problem, and I was asking me, what's an example of something I could do that doesn't utilize calculus? It's a pre-calc class, but it utilizes some of these trigonometric identities, and one of them told me that I could probably use AM radio, amplitude modulation radio, and that would be a relatively basic example. So what's the concept here? Well, so we have two trig functions added together. Basically, we have two sinusoidal waves added together, and when you do that, you end up with a type of wave. It's called amplitude modulated wave, where you have a carrier signal. I'm sorry, a carrier wave and a signal wave. So if I have sort of a generic sine curve like like that, I'm using sine, but it should be cosine, but whatever. I'm not going to worry about that right now. Just the concept, the picture should be as simple as possible. So this is going to be what's called the signal. Now, if I copy this, if I reflect it across the y-axis and I get this reflection of it, I basically now have this space that is encapsulated by the sine curve and the negative of the sine curve. It's actually going to try to be cosine, but we'll just go with this. Now, within that, if I get a different color here, I can have a different curve within that, right? And this thing, that was a little wonky. Let's try that again. Doesn't need to be perfect, but we'll go with kind of good. Good enough, close enough. So this blue curve is called the carrier wave. The reason you might want that is if you just had that generic sine curve, and of course it would have a different amplitude or a different angular velocity to be the signal that you want. If you just sent that over the radio, you might have a number of problems. One, you might want to be able to send more than one signal over the same frequency bandwidth, and you have to have something to distinguish them so they look different. They can't all look the same, because how do you know which one you're supposed to be receiving? Also, you might have a problem where when you have a really low frequency wave, you might not be able to push enough wattage through your radio antenna to send that signal and get a good range of it so people 100 miles away can receive it. Again, I'm not an engineer. That's my basic understanding, that there are reasons you would want to do this. So as I was saying, that black curve is called the signal, and it's when you transmit just the blue curve, then through the air, you're just going to see something like this, right? And there's this implied signal. I didn't draw that very well, but bear with me. There's this implied signal that gets reconstructed on the receiver's end to find out what the signal is. Like, you'll have an agreed upon known carrier, you receive the overall transmission, and the computer goes through a calculation and it pulls out that signal, and that's how you hear things over the radio, right? That's more or less how it works. And AM radio works with this kind of modulation. So that's the basic concept. So given that this is our function giving the waveform, what is the period of the carrier wave? We can calculate that. So in order to do that, I'm going to copy the function down here because it's running off screen. So it's cosine 2t plus cosine 3t. In order to do that, we're going to need to use a sum to product formula. We're going to need cosine alpha plus cosine beta equals 2 cosine of alpha plus beta over 2 times cosine of alpha minus beta over 2. Okay. In this case, alpha is 2t and beta is 3t. Okay. So my function becomes f of t becomes, well, 2 cosine of 2t plus 3t all over 2 times cosine of 2t minus 3t over 2. Okay. Now I can simplify this a little bit. 2 cosine 2t plus 3t is 5t over 2. I'm going to rewrite that not as 5t over 2, but 5 halves times t. 5 over 2 times t. And then cosine of 2t minus 3t will be negative 1t over 2, which I'll write as negative 1/2 t. Okay. Now, I'm not going to end up needing this one. You'll see why in a second. But since cosine is an even function, I can just change that minus to a plus, right? In an even function, the sign of the input doesn't matter, so just make it a plus. So in this format, remember, notice this is equivalent to this. I've just rearranged the way it's written using the sum to product formula. In this format, this factor has a greater frequency, right? The amplitude, not the amplitude, sorry, the angular velocity is greater. This is the carrier component. Okay, this one, oops, why it's being difficult. This one is the signal component. Okay, so the carrier has an angular velocity of 5 over 2. Okay, so in order to find the period, I'm going to use the period formula, t equals 2 pi over omega, the numerator being whatever the standard period is for the trig function you're dealing with, and cosine has a standard period of 2 pi. And you divide by the omega from the function, so 2 pi over 5 halves, which is the same as 2 pi times 2/5, which is 4 pi over 5. And this is the period of the carrier wave in this example. So again, I just wanted to have an application problem, show you why would we care to have these formulas? Why do we even bother with them? Well, they're very useful for certain calculations. Engineering, physics, chemistry, math, just these different disciplines sometimes have uses, and especially electrical engineering, mechanical engineering, and civil engineering are going to use all of these identities at some point. And as I said at the beginning, don't worry too much. I think I said at the beginning, I'm not going to test you on this in particular, so don't worry too much. I just wanted to give you one example of what this kind of thing could be used for.